Good evening, PAD 316ers. So I've spent some time thinking about our last few classes, and I know that a lot of you are having a hard time making this big jump from talking about, these very concrete things like descriptive statistics, mean, median, mode, the interquartile range, and talking about probability and making the jump for how we put those together and how we get to statistical inference. And I understand that this is a really tricky topic because it's a tricky topic, I think, for any student of statistics, especially for those where this is the first time that this idea is really being presented. So in terms of our class, I've thought about, what do you guys really need to know? As policy analysts and as future public managers, in order to be able to do a really good job? What do you need for the job market? And what can we try to trim away to take away some of the confusion about this topic? So I think what really happened in the last few classes was that we had a lot of math, which is not really tough because you guys can do the math. I've seen you do the math. I think it's all the formulas and the letters and not really being able to connect the concepts and the theories to why we're doing the math. So what we're actually going to do today in this mini lecture is to take a step back and we're going to look at the big picture. And from looking at the big picture, we're going to circle back around and talk about why these distributions, why the different distributions that we're talking about in class are so important. So I'm hoping that we can do this in less than 45 minutes. This would be a good mini lecture to listen to and watch maybe with a cup of coffee and your Excel open next to it. But please email me questions or concerns after this mini lecture is done. So I'm actually going to start off by talking about an email that one of your classmates sent to me. And the reason that I'm starting with this email is kind of framing our big picture is because I think a lot of you are struggling with the same question. So the specific question starts off with the student saying that they know it's a good idea to take samples because it's more realistic to gather data from samples than it is to get data from an entire population. This is something we covered in the first half of the semester. The student also says that they know that if we compare the sample mean to the population mean, they should be fairly similar as long as we have enough samples. The confusing part is the whole purpose of gathering samples is because it's too unrealistic to gather data from the entire population. So how can we even compare the two if we can't get all of the population data? How can we know what the population mean is if the whole reason for taking a sample is because we do not have the information for the entire population? And this is such a fantastic question because you're bringing together what we've been talking about in terms of sampling design, right? And the point of sampling design is to get a representative population so that you can say something about the larger population based on that sample. But we need to take it back actually a couple of steps in order to really get into this question. And how we're going to do this is by going to the big picture. Now, I think that you all can probably see this slide right here. This, is the big picture for what we're learning in class and actually what we've learned to this point in class. So what you've learned so far is about the sample size down here. You've learned about the normal distribution. You've learned about shape, center, and spread. And this is kind of where we stopped in the beginning of the semester because everything else was about describing the data in the sample or in the population and talking about probability. Okay, so what we're actually doing, the big picture with the statistics, is that what we want to do is to be able to get to some understanding about the population, okay, the entire population, this big box right up here. And we know that the population is described by certain population parameters. Okay, but typically we don't actually have information about the entire population. And this is for a variety of reasons, because it takes a lot of time and it takes a lot of money, and sometimes it's actually impossible to get complete information about a population. However, we know that from the population, if we take a representative sample, we are able to calculate some sample statistics. And these are those funny words that I was talking about, right? The p-hat, which is the sample statistic that represents the probability, x-bar, which is the sample mean, and also r, which is the correlation between two sample variables. All right, so we know that we want to get to the population. We know that we get samples from the population. We know that from the samples we get sample statistics, and we know that in order for our sample statistics to be any good, we should be considering the variability in our sampling, okay? And we've talked about this a little bit, and the reason that we're concerned with variability is because if you have too much variability in your samples, when you're taking lots of samples to try to figure out what the true mean is of a population, the true statistics, you're not going to get very good results. You're not going to be very close to those of the actual population. Okay, so with sampling variability, we're also concerned with bias, but we can kind of get to the sampling variability by understanding our sampling distributions. Okay, and this is what we're talking about. We've been talking about in class. This has been the main focus of our discussion. And the sampling distributions tell us about the underlying process that's creating these variable values, that's creating the values that we see in our data set that are representative of the true population. Okay? And so we talk about our sampling distributions in terms of their shape, in terms of their spread, and in terms of their center, right? So you guys know all this. The center is the mean and the median. The spread is the variance, the standard deviation. We've learned about standard error as well. We know about z-scores, which are all measures of spread. And then we know about shape. What is the mode? Is the shape symmetric or is the shape non-symmetric? So these are things that you all already know, right? And all of those things, so the center, the mean and median, the spread, the variance and standard deviation, and the z-score and the standard error and the shape, these depend on the sample size, okay? So the spread, getting an accurate idea of the spread really depends really heavily on the sample size. And getting the right shape of our sampling distribution depends on whether it's normally distributed or if we can get it close to being normally distributed. And the center, okay, the mean and median, is actually what links us all the way back up here to our population parameters, right? The true values of the population, the true value of the population mean, the true value of the population probability that we're really interested in getting, okay? So I know that was a lot. I want you to take a pause and either play this part of the video back as we're talking through it, highlight some areas that seem confusing to you, but just kind of look at the chart. And this really tells you what we're trying to get at when we're using sample statistics. Because basically what I'm saying is that this part of the screen up here, the population and the population parameters, in real life practically are unknown. Okay, but we know that there is some connection between the population and our sample, right? And the sample is characterized by these features down here, center, spread, and shape, which depend on some characteristics of the sample, okay? So going back to the question that your colleague asked, how can we even compare our sample to the population? Well, it's not really a question of comparing the sample to the population. It's a matter of knowing that there is a relationship that exists between the sample, if we've done our sample correct, if we've done our sampling correctly, and the true value for the population. And because we know this relationship exists, and because we know that there's certain rules that govern that relationship, we can take advantage of that to go from our samples into inferences about populations. Okay? So we know generally about samples. This is what we can get. This is the data we know right down here. And we're trying to use it to back up into finding generalizable information about the population. All right, so we're going to get a little bit more into this. And I think that this may become more clear. Okay, so our next slide is showing you the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things that you must know. Okay, this is the big jump from samples to populations. These are the logical propositions, these are the logical assumptions that we need to accept as true in order to think that there's any validity to what we're doing in connecting samples to populations. Okay, so here goes. Samples are selected from populations. You all know this. We try to do random samples to eliminate bias. And when we're talking about taking lots of simple random samples in order to get to the true population value, what we're doing is we're trying to decrease variability, which we'll touch on a little bit later. The second thing we know is that populations or population distributions are described by parameters, and we assume that these parameters are the true values for the entire population. And we don't have this information, okay? We're getting it, we're backing into it from our information from our simple random samples. The parameters, so these population parameters, are constant in value, they don't change. Our samples are described by statistics. This is just saying that we can describe our samples with a sample mean, a sample standard deviation, which is the standard error, and we have these tools that we can use to describe our samples, focusing on center, spread, and shape, which you all already know from earlier in the semester. Statistics are variable quantities. Okay, this is key. Our true population, our population parameters are constant. They do not change. The real value of, let's say, the real value of weight distributed across the US doesn't actually change, right? The mean value doesn't really change. The statistics, though, because they're based on samples, will change sometimes substantially from simple random sample to simple random sample, or from a random experiment to random experiment. However, what we do know is that if we take lots of simple random samples, or if we take lots of random experiments, we can create a distribution of our sample statistics, and this is known as a sampling distribution. We know that the sampling distribution of the sample statistics is approximately normal. So if I take the means from 80 simple random samples, that shape, that distribution of the mean is going to be approximately normal, and that's really helpful. We know that the sampling distribution of the sample statistic is characterized by shape, center, and spread. We've spoken about this before. And we know that the spread of the sampling distribution is related to the sample size, right? So the larger our sample size, which is a sample size of simple random samples, actually, when we're talking about the distributions of statistics, is really related to how many simple random samples we take. This is the central limit theorem that says the more simple random samples that we take, the more we're going to decrease the variability in our data, and the more our sample mean is actually going to closely approximate the true value in the population, which is what we're looking for. Okay? And the key here is that the sampling distribution is centered at the population parameter. What that means is that if we do our sampling correctly, if we take lots of truly random samples, and if we take enough truly random samples, the distribution of our statistics, and the key statistic here is the mean, is going to be centered at the population parameter. So all this means is that the mean for the sample, if we have a sample distribution, will be the same as the mean for the population. And from there, we can do a lot of different things with inference. So I want you all to take another pause here and think about these propositions, okay? Do they make sense to you? If they don't make sense, make sure to write it down in your notes or email me at the end of this presentation. So another way to think about it, and you all have seen this visual before, is that we have an entire population that we want to know something about, okay? But we don't actually have the true values for this population, okay? For a variety of reasons that we've discussed before. But from this population, if we take enough simple random samples, we can make some inferences about the population because we know something about the relationship between the population parameters, so the values that are true to the whole population in here, because of their relationship to those statistics in the sample, okay? And the most important one is the mean, okay? Because we can figure out that the mean of a bunch of simple random samples that we take over here is actually the same as the mean of the population, all right? So let's let that sink in for a second. Take a break, write your notes, do what you gotta do. The next part of this mini lecture is really gonna focus on some things that you already know. And we're gonna go over them pretty quickly so that we can get into the good stuff. Okay, so here's the good stuff. Why the normal curve matters, why it's so important that you all understand what the features of a normal distribution are. And it goes beyond just knowing whether the probability of a single event, being able to get that from a density curve or from a normal distribution. The normal curve matters because, as we've demonstrated earlier with our propositions, the sampling distribution of the sample statistic is approximately normal. So if we can go from the sampling distribution of the sample statistic to understanding the true parameters of the population, it's really important, right, to remember the features of our normal distribution, because that can actually tell us how close or how far off our estimates are from the true value. So we're going to get to that. But normal matters, right? Because we know that the sample statistics are normally distributed. And we use those sample statistics to tell us what the normal parameters, what the population parameters are. So you guys remember, density curves are basically just smooth versions of a histogram, where the x-axis is the value of the variable or the count of the occurrence of a variable. The y-axis is the probability of the observation in the data, and the area underneath is equal to 1, and it describes the overall pattern of the distribution. We know that in density curves, normal curves are symmetric, which means that the mean and median are in the same location. They're right at the center, which gives us some useful knowledge about where the observations fall, right? Where most observations will fall. What we do with that, some of the tools that we can get from our knowledge of the normal distribution, is not only knowing where observations will fall within one standard deviation or two standard deviations, but we can also talk about specifically where a variable is within the normal distribution. And we know that there are some, you guys are really familiar at this point with standardizing variables. We standardize variables that have a normal distribution using the z-score. So that z-score is going to come up again and again as something that's really important. And it's important because we give our variables really specific values when we standardize them. They have a mean of 0 and a standard deviation of 1. So as I said in class the other day, this actually means that our z-scores have a normal distribution. So this is kind of a tricky thing to get your head around, but you can think of a z-score as a statistic, okay? A statistic that has a normal distribution. Because we are talking about, let me take a step back. So z-scores are really important in terms of talking about where observations lie and also where our sample statistics will lie in a normal distribution. So moving on from there, thinking about what exactly a normal curve is giving us. So we know that the area under the curve is the probability that an event will happen. And by talking about specific areas, we can get an idea about how likely or how unlikely it is that a value that we have is actually a true value, right? So what I mean by that is let's think about a situation where we know something about the distribution of okay, let's do a specific policy example here. So one of the things that the U.S. government does is to monitor communications between individuals that could potentially lead to a terrorist attack. So one of the things that they use as an indicator of the potential of an attack is once they've ID'd individuals as people who are involved in terrorism, they evaluate the rate of communication, how many emails or how many messages are sent back and forth. So what we're doing is we're measuring the rates of communication between individuals, and we know that the communication is normally distributed, right? And it's got a very specific mean. On an average day, people are only exchanging about 12 emails when there is not a terrorist event that is about to occur. We know that there is a standard deviation in terms of the amounts of emails that is approximately 10, okay? So one of the questions that we might ask is, what is the probability that that the individuals that we're looking at will exchange emails on a normal day, that they will exchange more than 60 emails? Okay, now the implication there is that if they are exchanging more than 60 emails, something is about to happen, or maybe not about to happen, depending on where it falls in the distribution of our emails in this hypothetical example. So what we would do is we would look for the mean, right, which is 12, and the standard deviation, which is 10, I think I said. We're going to pretend that I said the mean was 12 and the standard deviation is 10. Okay, and then we would try to figure out if 60 emails falls within 1, 2, or 3 standard deviations of the center, which would tell us how likely or how unlikely it would be that this amount of emails would take place in a normal day. Okay? So I want you to take a second and to write that down, that we have a policy scenario with emails. The average email is 12. The standard deviation is 10, and we want to know if 60 emails is outside the realm of normal possibilities. All right, so you all have written down somewhere that the mean is 12, the standard deviation is 10, and we want to know the probability on any given day that the number of emails or our X variable is going to be greater than 60. Okay, that's all we're asking here. So the way that we can figure that out is to actually go to Excel, and we can figure out the area under the curve that goes from 0 to 60. Okay? So we're going to do our formula equals norm distribution. We're going to put in the value that we're interested in, which is 60. We're going to put in the mean, which is 12. We're going to put in the standard deviation, which is 10, and we're going to write true because it's cumulative. Now, that gives us 0.9999999, okay? But that is just the area under the curve that goes from 0 to 60. What we're actually interested in this case is anything that goes over 60, or that's at 60 or above. So in this case, what we need to do is say 1 minus 0.9999999. And this is actually what gives us the probability of getting more than 60 emails on a normal day. And what you'll find if we make this smaller, is that that's very close to 0. Now you can think about that, and that's what this just, the 8e to the negative 0.7 means. It's just incredibly tiny. What that means is that if we look at our curve, the probability that it's greater than or equal to 60 is out here in this little area, okay? So all the other observations, all the other values are in this area, which is the 0.99999. But we subtract that from 1 in order to find this small area that's over here. Okay, so that's one example, and you guys can work along in Excel as we're doing these examples. I'll post the examples on the course Blackboard page along. Okay, so to briefly recap, what you do in step 1 is you find the probability of getting between 0 and 60 emails using Excel, and that function equals norm.distribution. And then you subtract the probability that the value is between 0 and 60 from 1, right? Because you can't have higher than 1 for probability. And that gives you the probability of getting more than 60 emails. And that's what we did right here. Okay, moving on. So we know that the area under a normal curve is the probability that an event will occur. We talk about the probability of an event occurring as the probability of x being greater than or less than some value. And we do this because there are infinite possibilities when we're talking about normal distributions, because they are technically continuous distributions. We calculate this under the curve using Excel. We also did an example in class where we used our book. But I will not be asking you to use the book to find these values. So actually what we're going to do next is to talk about another way of representing probabilities. So in class, we worked through the example where we were looking at a normal distribution of exam scores that had a mean of 84 and a standard deviation of 8.3. In class, we asked the question, what is the probability that any student got an exam score greater than 93? In this lecture, I'm going to ask you, what is the probability that any student got an exam score between 83 and 93? So the probability that our random variable x is between 83 and 93. Okay? So, yes, here we go. So what we're going to actually have to do here is to work through our problem using our knowledge of math. So we have two parameters here. We have two things that we have to figure out. We have to figure out the probability that any student gets an 83. We have to figure out the probability that any student gets a 93. And we have to use that knowledge and our knowledge of the area under the curve to figure out what scores fall precisely in that area. Okay? So we're going to use our function equals norm distribution. And so our first value that we're going to talk about is 83. The mean is 84. The standard deviation is 8.3. And we're going to put true. Okay, and for this example, we have a probability of 0.452. So what this is telling us is the probability that a student gets a score between 0 and 83. Okay? So the next thing that we're going to find out is the probability that any student gets a score between 0 and 93. Okay? So we just need to use our function again, equals norm.dist. Okay, we're going to put in 93 this time because that's what we're looking for. The mean is still 84, the standard deviation is still 8.3, and we're doing true because this is cumulative. All right. Okay, and we get 0.86089. So I have a few things here. I have the probability that the values are between 0 and 83, and I have the probability that the test value will be between 0 and 93. So what I want you all to take a second to think about is how do you go from here to finding the probability between 83 and 93? Well, we can't just subtract it from 1, right? Because we have two values, and if we subtracted this value from 1, we would get the probability that anybody got a value that was greater than 83. And if we subtracted this value from 1, we would get the probability that anybody got a score greater than 93. Okay, but that's not what we're looking for. We're looking for between 83 and between 93. So how do we get there? We're actually just going to subtract 0.86089 and 0.452 to find the area in between, because both of these contain the interval of 0 to 83. Okay, that's 0.452. So if we subtract that interval from the interval of 0 to 93, that gives us specifically the interval between 83 and 93. So just some simple math. It's pretty logical, right? And we find the probability that any student's score is between an 83 and a 93 is actually about 41%. Okay? So this is the probability that the score is between 83 and 93. And that should be, there we go. No, not x is greater than that. Okay, there we go. All right. So there's an example of how to think through using the normal curve in order to figure out different probabilistic outcomes. And in this case, we were using a very simple event, so the distribution of test scores, but you could also use it to talk about sample statistics, which we are going to move on to next. So I think I've driven the point home enough times that when we're talking about statistical inference, what we're doing is we're taking our knowledge of data analysis and we're taking our knowledge of probability and we are using them to make this big jump from taking limited knowledge about samples to making big, broad generalizations about populations and what population parameters are. So I'm going to just leave this slide in here. Limited data, our limited data is our samples, okay? And this can be one sample or this can be many, many samples. What we want to do is to make informed inferences about populations based on our limited data, which are our samples, okay? And we do this, let me make this more clear, by understanding the sample distribution. Okay, this is the key, this is the link of how we get from what we have to what we want. Okay? So this is just a reminder that when we're talking about populations, we're talking about parameters, and when we're talking about samples, we talk about statistics. Just match up the first letter, population, parameter, statistic, sample. Let's see, I'm going to take this out because we've already been over it. So you all remember this lovely picture from class where we talked about making the jump from talking about one variable. So here this variable is the call lengths. This is all of the call lengths in a population that we're working with, to talking about sample means. And this is an illustrative example. A lot of times we don't actually have the population value. In fact, most times we don't have the population value. This is one example when we have a known population that was meant to help you understand the proof, to see exactly what the relationship is between the population and the distribution of our sample statistics. And here it's specifically the mean. So what we know is that if we take our population, which in this case has more than 30,000 individual units of observation, and we take multiple random samples from that population, if we go over here and we take each mean of those simple random samples and put them on a histogram, they're going to start to cluster and they're going to start to take on a normal shape. The more simple random samples that we take from our population to put into our little histogram over here, the more this is going to start to look like a normal distribution. And in fact, the more simple random samples that we take from over here to put into our histogram over here for the sample mean, the closer the mean of all of our simple random samples will be to the actual sample mean, which is over here. Okay? So that's all we're doing with this picture, and that's the core, right? That's the activity that we're doing. This is how the sausage is made for moving from samples to populations. This understanding that if we take enough simple random samples from a population, we will get a normal distribution, and the mean of all of our samples is going to be equal or very, very close to the mean of our entire population. So with that in mind, I'm going to take out this because we've talked about that and I think it's probably confusing. And let me take a second to reorganize here. I'm just going to take a quick pause. Okay, so what we've covered in this past slide to make that big jump between sample statistics and population parameters is the return of the central limit theorem, which basically tells us if we have enough simple random samples, if we have enough observations, that we're going to get a normal-like distribution, and that the mean, our measure of center, is going to match that of the population. That's all that that's saying. And as I've said before, that is the key to statistical inference. But when we are talking about statistical inference, there are a couple things that we really need to consider. Okay? So it's not enough just to take some simple random samples, and it's not enough just to take some information and call it a sample and say, okay, I'm going to make some connection here to the population. You need to consider bias in your samples, and you need to consider variability. Okay, and we've talked about how we can address bias, right, which moves our values from their true center which means we'll get wonky means. So the means of our sample will not actually match the means of our population. We need to address that. So how do we address bias? Well, you guys should know this. We randomize, right? We remove bias by randomizing, by mixing the population enough so that every sample we take is an approximate representation of the true population. All right? The other thing that we have to consider when we're talking about this big move between samples and populations, or populations and samples, is variability, okay? And variability is talking about the distance or the spread between our samples, okay? All those samples that we're taking, all of the samples that we're taking from our population and putting over here, we're going to have a large amount of variability if we don't take enough simple random samples. So what we do to address variability, which also makes means wonky, and it makes it harder to give a precise mean. We'll have, maybe a guesstimate of what the mean is. In order to address variability, we take lots and lots of simple random samples. Okay? So that is very important. There's a lot of yelling on this slide in terms of capital letters, and I'll even take it to the next level, and I'm going to bold this. Because what we're saying is that we know there's a connection between the sample and the population. We know how to make that connection through the mean, because the mean of the sample distribution will be equal to the mean of the population, unless we have bias and high variability in our sample distribution. Okay? So we address bias by randomizing, making sure that our simple random samples or our experiments are randomized a lot. That's why we spent so much time talking about research design earlier in the semester. And variability, which means you need to take lots and lots of simple random samples so that you have a lot of data that shows the clear relationship and the clear shape of the distribution. Okay, so again, how to reduce bias and variability, random sampling, and large enough samples. And I'm going to take this out because we don't need this right now. All right. So at this point, I am going to take a pause, and I'm going to encourage you all to take a pause and think about what we've just discussed. And I'm going to post a second video lecture talking specifically about different kinds of distributions. So you guys know at this point that the normal is really, really important. You know how to calculate intervals and the probability that an interval will happen, like a score between 83 and 93. You know how to find the probability that a specific value will occur, like the probability of getting a 93 on a test. What we're going to do in the next mini lecture is to expand that, because not everything is always normal. Okay, there are a few special cases that we need to consider, and that's what we're going to do, talking about binomial and talking about Poisson. Okay, so stay tuned for the second one, and I will talk to you then.